Okay, so now we're looking at section 6.3. And here we're dealing with some more probability rules, basically. So probability rules or probability techniques, ways of calculating the probability of various events. So let's start from square one. So if we want to define what it means to calculate the probability of a certain event E, using only mathematical reasoning, we could give the following definition. So given an event E, we say that the probability of the event E occurring is equal to the number of ways to get the outcome E over the size of the sample space. So the cardinality of the sample space. So really, if you just think about these in terms of sets, all this is saying is that the probability of the event E occurring, which remember is a subset of the sample space. So the probability of E occurring is the cardinality of that subset over the cardinality of the entire sample space. So it's given by that ratio. So let's look at an example. Suppose we want to calculate the probability that out of 2 coin flips, you will get at least 1 heads. So we want to calculate this probability. So in order to do so, we really need to focus on this word at least. And in fact, this sort of wording tells us that we're dealing with what we call an at least probability. So what does it mean to have at least 1 heads? So let's look at the sample space first. The sample space of this particular experiment consists of all the outcomes that we can have if we flip a coin twice. So that could either be heads, 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 tails, tails, heads, or tails, tails. So these are all the possibilities. Now the event E as a subspace consists of all those events or outcomes within the sample space that have at least 1 heads. So that includes heads, tails, tails, heads, and heads, heads. So having more than 1 heads means that you qualify for having at least 1 heads. So we can see that E is a subset in the set sense of S. So if we want to calculate the probability that E will occur, then we're simply taking the ratio of the cardinality of the subset E over the cardinality of the sample space. And we can see clearly that E has 1, 2, 3 elements, and S has 1, 2, 3, 4. So this is our probability. So as I was saying, this particular section just is teaching us some techniques for calculating probabilities. And depending on the event that we're investigating, there can be some nifty tricks that we can use to make the calculations simpler. And one of the most useful is the complement rule. So, complement rule. We've learned about complements in the context of sets. So remember that if we're dealing with a sample space S and an event E, then the shaded region here is the event E, and the shaded region here is the event E complement. So everything outside of E. So this is E, and E complement is everything outside. So we're going to use this idea to help us calculate probabilities. So what this whole rule hinges on is a basic fact, which is this. So basic fact. If we're interested in the probability of the event S, where S is our sample space. So if we're interested in this probability of the event S, which is to say we're interested in the probability that S will occur, which is to say anything will occur, because S includes all possibilities. So the probability that anything will occur within the set of all possibilities should be 1. We have 100% chance of something happening. We can see this in another way, that the probability of S by definition should be the cardinality of S over the cardinality of S, which clearly is 1. So this is a basic fact that we can use when we're calculating the probability of a complement. So what's going on here? What is the complement rule and how does this play into it? So here's how this works. If I want to know what the probability of E is, but suppose that I have a hard time of calculating that directly, then there's another way of calculating it. In particular, I take the probability of S and I subtract away the probability of E complement. So to see that this is equivalent, let's first simplify this and say we know what the probability of S is. We showed up here that it's 1. So this really boils down to the probability of E is equal to 1 minus the probability of its complement. Now we can see that up here. If I want to know what E is, either I can calculate it directly, or I can find the probability of S, which is everything, and then subtract away everything that's not E, which would be equivalent to E complement. So if I take S and remove E complement, all I'm left with is E. And so this idea is applying to the probability here. If I want to know the probability of E, I can just take everything and subtract away everything that's not E, and we get the same thing. So let's look at an example. So how does this complement rule help us? Okay, so let's consider this example. Suppose we want to figure out what the probability is that out of 3 consecutive rolls of a die, at least one of those rolls contains a 5. So this is the probability that we want to compute. Now, again, notice the word at least. This is the operative phrase here that we want to look out for. This tells us that this is an at least probability, and sometimes it's best to approach these at least probabilities using the complement rule because it's too complicated to directly calculate it. So what do we want to solve? We want to find the probability of at least 1, 5 in 3 consecutive rolls of a die. Now, that means that I would have to find the probability that there's a 5 on the first roll, or a 5 on the second roll, or a 5 on the third roll, or maybe there's a 5 on the first and the second, but not the third, or maybe there's a 5 on the second and the third, but not the first, or maybe on the first and the third, but not the second. You can see how complicated this gets. In order to consider all possibilities, I have to think about all of the particular outcomes, and that can be complicated. So instead of doing it that way, let's use the complement rule. So if I rephrase this using the complement rule, then this probability should be equal to 1 minus the complement of at least one 5, which is equivalent to no 5s. So if there's not at least one 5 out of the 3 rolls, and that means there are no 5s out of the 3 rolls. So the complement rule says that this probability should be equivalent to 1 minus this probability. And what's good here is that there's only one way to roll 3 times and not get a 5. Or no, I should correct myself. There's not just one way, but that it's easier to figure out the number of combinations that do not include a 5. So let's think about this for a second. How many ways can I not get a 5? I want to figure out P of no 5s. So we're going to use the trick that we learned back in chapter 5. If I want to figure out all the ways that I cannot get a 5 in 3 rolls, then what I really have going on here is there's 3 slots that need to be filled. The first slot contains no 5s. So that means it can be a 1, 2, 3, 4, or a 6. So that's 5 possibilities. The second slot can also not contain any 5s. So it can be 1, 2, 3, 4, or 6. So 5 possibilities. And same for the third. So 5 times 5 times 5 tells me the number of ways that I can roll a die 3 times and not get a 5. To find the probability here, I need to take that number and divide it by the total number of ways that I can roll 3 die. So that's 6 by 6 by 6. Because I'm not restricting myself to the case where there are no 5s. So there are 6 possibilities for each of the 3 rolls. So if I compute this, then I get 125 over 216. So that's the probability of getting no 5s. So if I want to put this together with what I was trying to originally figure out, the probability of getting at least one 5 should be equal to 1 minus 125 over 216. Which is 91 over 216. So this is the number we were looking for. So that concludes section 6.3.